What's up, guys, and welcome to this video walkthrough of question 6 of the 2015 IEB supplementary exam, the physics paper 1, and we are going to do question 6 on fields. Okay, before I do that, here are our equations that we need for this section as well, but this is mostly just going to focus on those last few equations, but let's get into the first question. Okay, so it says, Mercury, the smallest planet in the solar system, has a radius, okay, so here's our R, of 2.44 times 10 to the 6 meters and a mass of 3.3 times 10 to the 23 kilograms. Calculate the magnitude of the acceleration due to gravity on the surface of Mercury. Okay, so question 6.1.1. Okay, so it's looking for the G, or the gravitational force. Okay, so we're focusing on this equation right here. So G is equal to the gravitational constant times the mass of the planet, so the mass of Mercury, over the radius of Mercury squared. Okay, and all we need to do is substitute values in now. G is a constant which is found on the formula sheet and has a value of 6.7 times 10 to the minus 11 times our mass was 3.3 times 10 to the 23, and the value of R, remember to put it in brackets when we're squaring it, is 2,44 times 10 to the 6 squared. Okay, and putting that into a calculator, we get a value of 3,71 meters per second squared, because that is the value of acceleration. Okay, and again it asks for the magnitude, so we don't have to give a direction. Cool, so that's the first question. Okay, moving on to 6.1.2, it says calculate the weight, calculate the magnitude of the weight of a 250 kilogram spaceship on Mercury. Okay, so we know that the force of weight, or Fg, is equal to the mass times the gravitational force. Okay, usually we say that the gravitational force is 9.8, but that is for Earth. Okay, but this is for Mercury, so it's the value that we calculated, and the mass is still 250 kilograms times 3,71 meters per second, and that gives us a value of 228.43, and the value is in newtons because it is a force. Okay, and again it asks for the magnitude. Okay, cool stuff. Yeah, so now we can go to the next question. Let me just give myself a little bit of space. Don't know if that worked. No, it did not. Okay, there we go. Okay, so the next question, 6.2. The diagram shows a conducting sphere X of radius, so that's R, in, I'm going to write this in meters, 0.4 meters, carrying a charge of 6.4 times 10 to the negative 8 coulombs. The sphere is at the top of an insulated stand which is placed on a digital balance. The weight is shown there. Okay, cool stuff. So we've been given all the information. I'm just going to write here that R is equal to 0.04. Okay, so it says, the first question, 6.2.1, says draw an electric field line diagram to represent the field set up by the sphere. Okay, so the most important thing here is the direction. Okay, so here we have a sphere X, and it's got a positive charge, so the arrows are going to point outwards. Okay, so we have something like that, and that's about all we need to do. And there we get our beautiful 3 marks. Okay, and here we got those marks as well. Cool stuff. 6.2.2. Okay, calculate the magnitude of the electric field strength at the surface. Okay, at the surface, it's very important, of the sphere X. Okay, so which equation are we going to use? So what are we searching for? The electric field strength. Okay, the electric field strength is denoted by this equation right here. Okay, so which equation are we going to use? We don't really know the value of F, so we're going to use this equation right here. E is equal to KQ over R squared. So the electric field strength is equal to KQ over R squared. Okay, and K, just like G, just like this G here, K is a constant. Okay, and it is found on the formula sheet. So we know everything, if I'm correct. Yeah, everything is known, so we can start substituting values in. So K is 9 times 10 to the 9 from our formula sheet, times the value of Q is 6.4 times 10 to the minus 8 over R. I'm going to write that as 0.04 squared. And the value of E is then equal to, if we plug this in, it's equal to 360,000 units of newtons per coulomb. Okay, and there we have E. Again, most of these questions are following the magnitude. Okay, the next question says 6.2.3 says that another sphere Y carrying a charge of negative 4.8 times 10 to the minus 8 coulombs is held so that its center is 60 millimeters vertically above the center of sphere X. Okay, so how are we going to do this? Okay, let's draw a little diagram quickly. So if this is sphere X, okay, here we go, and it's on its nice stand. Okay, so sphere Y is held, the center distance between them is 0.06 meters, and Y has value of minus 4.8 times 10 to the minus 8, X has a value of positive, what was the value, 6.4 times 10 to the minus 8 coulombs. Okay, so there's a quick sketch of what has happened now. And okay, so it says calculate the magnitude of the electric force on the sphere X. Calculate the magnitude of the electric force of a sphere X on sphere Y. Okay, so what are we going to do? We're looking for a force, right? So we're looking at, let's clean this up a little bit. We're looking at this equation right here. We know the value of K because it's a constant. We know R, which is 0.06, and we know Q1, Q2. So Q1, Q2 of these values right here. We can label one of them Q1, we can label the other one Q2. So the force is equal to K, Q1, Q2, Q2 over R squared. Substituting values in, we have 9 times 10 to the power of 9 times, okay, I'm taking magnitudes for all of them, 6,4 times 10 to the minus 8 times 4,8 times 10 to the minus 8 once again, all over the distance, which is 0,06, and all of that is squared. So we know that the force F is equal to, if we plug this into our calculator, we get 7,68 times 10 to the minus 3, and the value, the units of newtons. So that's the force that sphere Y exerts on sphere X. Okay, and then it says calculate the new reading of on the balance. Okay, so we know the existing reading. This value right here is the existing reading. Now the question that we need to ask ourselves is the force of Y being exerted on X pushing X down, or is it moving X up, right? And so let's try and answer that, right? So we have a positive and a negative value, right? And opposite charges will attract each other, right? So Y is causing an upward force on X. So the new force, or the new balance, again, noting that this is in units of newtons, right? So the new force, the new reading on the balance, let's do that right here. So that was question A, this is question B. Force new is going to be equal to the old force, which was 9,54 times 10 to the minus 3. And now we said that that force, so this is the old force. The old force was pushing down. The force of y is now pulling x upwards, so we're going to say minus. Okay, and we're going to minus the value we just calculated, 7,68 times 10 to the minus 3, and our new force is going to equal 1,86 times 10 to the minus 3 newtons, or 1,86 millinewtons. And that would be our final answer. So the new scale would read that value. Okay, if, let's say hypothetically, if both of these charges were positive charges, then the force that y exerts would now be downwards, and our new force would be the old force plus the force of y. Okay, in this case it was the old force minus the force of y, but if they had the same signs, then the operation would also change. Okay, cool stuff, and that is the end of this video. I've done all these questions. Yeah, so 20 marks. Okay, cool stuff. Thanks for watching, guys. Hope it was useful.